It is my great pleasure and honor to introduce Mr. Alexander Andersson, and please help me welcome him on stage.
Yes. Hi, everyone. I'm Alexander. I'm a principal forensic consultant at Truesec. And I'm going to tell you a story today that starts on a dark place on the internet. It's a crime forum called XSS. Maybe some of you know about it. A user there, he posted a post that said something like, I built this ransomware builder, and I decided to distribute it for free. And he hosted it on his own GitHub. And this Git repository is down for obvious reasons, but in Web Archive you can find it looked like this. And this was sometime in June 2021. The history of this, if you look back a bit, you can correlate this with the same individual that also created something called the Bagley wiper. And I say wiper because these early versions of this ransomware was actually just overwriting every file on the system. It actually didn't even try to encrypt anything. And it was also called Ryuk in the early days. This, maybe you know about Ryuk ransomware, right? But this is not related to that at all, which people on that crime forum was pretty quick to point out that he was like, you know, pretending to be something he's not. But so then he rechanged the name to Chaos Builder. And after a while, there was actually encryption implemented. So they started using AES and then RSA to encrypt the AES keys. But with a small, like, you know, they only encrypted files that were up to 2 megabytes. Everything else they still just removed. So it wasn't really a ransomware, right? It was just, you know, destroying everything. So, you know, what happens when you start publishing a ransomware builder that anyone can use? We started following this, and I don't need to go into detail. I'm just going to show you an example. So this is Azovstal in Ukraine. And part of the kinetic war against Ukraine, there was actually this ransomware used. And on the other side, you have a kids game where kids are trolling each other and encrypting each other and selling the decryptor on this Roblox, which is a kids game. So, you know, that's kind of the full spectrum, right? And this really shows like how this keeps evolving over time. And what made this like take them into the next step was that there was actually some organized cybercriminals starting to use this. Onyx or VSOP is one of them. So this is from their, you know, every ransomware group has this like blog where they post the victims and all sorts of things. There was also the other ransomware group called Solidbit. And finally, also, our favorite Killnet also started using this. So when we come to like October 2022, we see that this is used all over the place. There are several different threat actors not related to each other. And this is pretty much where we come into the story. So this is a picture of Germany. It's because the company that calls us was from Germany. And I'm going to try to show you like what their machines looked like. So, you know, they're calling us, and, you know, this is the kind of ransomware group that will escalate the privileges, become domain admin, then create like a GPO to push out the ransomware to everything in the entire environment. So this is my machine here. I have a Onyx XE ransomware. So let's rename that. And then we run that as admin. Are you ready? So I should tell also that my malware environment broke pretty recently, so I haven't really tried this. I hope I'm not destroying my actual computer now, but we'll see. So I have a few files here. I guess this takes a short while. So I have a few files here, and they're gone. So it prompts for that, you know, they create this README file. You need to go to this Tor address, blah, blah, blah. I guess you all have seen this. But the different versions that each group have. If we actually look at this one, which is the presentation I'm doing today, it's going to look not like a PDF file, right? So a PDF file would start with PDF, %PDF something, blah, blah, blah in the beginning, right? If we try to open this, it's just, yeah, destroyed. Maybe we can try to open it with an actual reader. So I don't know, Firefox. And it's just broken. So, yes, that's where we came in. And you can imagine, like, this is just my virtual machine, right? But that is pretty much what their entire infrastructure looked like, which isn't a great situation. So if you search for chaos ransomware, because like we quickly identified and found the actual executable, and we saw that it looked like chaos. And we searched for it, and it said that it works something like this. So it has like this RSA encrypted key in the beginning, and then it has like, it stores the IV and blah, blah, blah. So it uses all like, the best practices. These are pretty much the same encryption that is used for, when you do banking or whatever. So what we saw, though, was that this one was a bit different. So they had actually changed the encryption scheme. So we figured that, yeah, this is definitely worth taking a look at if they change something else. And one of the things that they had changed was that they did not wipe every file over 2 megabytes, but instead they wiped every file over, I think, what is it, like 13 gigabytes. So that creates like a totally different situation, right? So some of the like larger important databases is going to be destroyed, but imagine all, the PDFs and Excel and blah, 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 Office documents, they're still going to be intact. And this customer in particular did not have any backups for the file server. So obviously, that's something that's going to be very interesting for them if we can get those files back. So we started looking into like how does it actually do the encryption. So this is the reversed function from the Onyx ransomware. And this is how it creates the password when it's going to encrypt the file. So it's a 40 character, the length is 40 characters, and it's random. It's going to be pretty hard to brute force that. The actual encryption is AES, and it's using these different things. Everything looks good, but wait, if we just go back, like what did it say? Said it random? Is that actually random? If we Google for that, it says that to generate a cryptographically secure random number, such as one to use for what they're using it for, use something else. Okay. So, I called my colleague Carl, who actually knows this stuff, and I asked him that, that system random thing, is that just a theoretical, mathematical, academic thingy, or, can I actually get files back? And he said, I actually got a POC because I, created a CTF a while back, and I have a POC for breaking that to my GitHub. So, yeah, cool, let's start with that. So, how would that work? Before we actually go into the details, let's just differentiate what's random and what's cryptographically secure random. If we take like a die and you throw a die, let's assume it's fair and it's going to be 1 to 6. That's random, right? But if I get 6 guesses, I'm always going to guess that random, right? So it's not really cryptographically secure. It's pretty easy for me to figure out what they had in that random. And it's sort of the same thing here, and we need to just understand like how it works. So we have a seed, which is some kind of initialization value that you give the random function. From that, it creates something that is supposed to be random. So not like based, like you should not be able to guess it. If you change the seed, you're going to get a completely different sequence, another seed, a different sequence, another blah, blah, blah. But if you do the same seed 2 times, you're always going to get the same sequence. So it's like actually based on the seed. That's what it starts everything from. It's actually the absolute value of the seed in this case. So if you give it a negative number and a positive number, it's going to give the same sequence. So what is the seed in this case? We're not as lucky as it's a die, so it's only 6 values. But it's an integer, which is 4 bytes. And it's only the absolute like positive values. So we only have 2 billion possible seeds, which means that it can only be 2 billion possible passwords for every file they encrypt. And, it's going to be pretty hard to do that manually, but if you put up a fairly good computer, that's milliseconds, right? So if we look into the encryption a bit more, we see that the first step is that they get the seed, they generate a random password, and they do this uniquely for every file. And from that password, they use something called a key derivation function. And that is basically just making it harder to brute force this kind of thing. And it derives a actual bytes for the key and bytes for the IV, which is the initialization value that you need, because AES is a block cipher. So when you encrypt the first block, you don't have a previous block, and then you give it a fake previous block, which is the IV. So it gives it that, and then it's the final step, because this is CFB mode. So the final step of this is that it's XORing, which is just a very simple mathematical function with the plain text and whatever you got from encrypting the key with the IV. So that's the actual ciphertext, and that's what's stored on the system when the file is encrypted. Okay? So one trick that we can use here to actually get files back is that we actually know the plain text. Well, not the full plain text, but we know the first bytes of the files, right? Because we have, for example, a PDF file is always going to start with the first 4 bytes. It's always going to be the same. And we only need a block, right? We don't need the full plain text to do that first guess. So we can actually roll that last step back. Because we know the plain text, at least we can guess the plain text based on the file extension. And we can go back to the stage of the encrypted IV. All right. So that key derivation thing, that's kind of heavy, and it's not fun to, do that derivation thing. It's actually made to make it as slow as possible. But we can, pre-compute a table with all those 2 billion possible seeds and whatever the encrypted IV is going to be if you have that seed. So we create this big table, and that's just going to be 8 gigabytes. That's not that bad, right? We can just iterate an 8 gig file. And when we implement the actual encryptor, what we do is that we read the first 4 bytes, we XOR them with whatever we guess that the plain text is. Then we calculate by XORing those to the encrypted IV. And after that, we look up the seed from this big 8 gigabyte file, and whatever index that is on is going to be the seed. And then we have the seed, and we can just do the same thing and calculate the IV and the key and blah, blah, blah. And there we have an decrypted file. So that's it. So we were actually able to restore quite a lot of files for this customer. And running this is really, really fast once you have done that initial pre-computation. But it's not that bad, actually. I could run it on my own computer and generate that in a few hours, because it's not that much. But the natural next question would be, can we actually crack this entire family, or is it just this changed sample that we happen to find? Or is it actually possible to break the entire suite? So we started looking into the original chaos, in that tree that we showed, that main branch of things. And it's a bit different because, well, one thing is that it actually uses 1,000 iterations of that key derivation, which is still very low, but it's just going to make our life way harder to generate any kind of table. And it's also using CBC. And that is important because the XORing part is before the key is used to encrypt. So that makes it kind of, we can't use that plain text trick. So this is going to be a bit harder, but, we can pre-compute the table with the password and the IV because we still have that integer limit, right? We only have 2 billion possible passwords. If we just pre-compute all that key derivation heavy thing, it's going to still be pretty quick to decrypt. And that's going to be 103 gigabytes. It's not that much, right? You can take the time to download a 103 gigabyte file if your entire environment is encrypted. Could be worth it. Problem is, on my computer, when I tested this, it's going to take 203 days to generate. And I don't have patience for that. So what do? I call Carl, and he knows CUDA. And Intel was very friendly and gave us a supercomputer. So we were able to actually generate this database with a GPU in under a minute. The major bottleneck was to actually flush things from the GPU memory down to the disk and stuff. So yeah, GPUs are awesome. And also Carl is awesome, by the way. He's very anonymous. That's why he's not here today. All right, so we're actually able now to break the entire family. At least the main branch of it. But there was this other thing also, the solid bit. which is a bit different. So when it comes to solid bit, it is a bit different because it's running the generation, the randomization thingy 2 times. The other one was just generating random bytes and then using that, so we only had like 1 int to go through. In this case, they actually random key and then random IV, which means that for every key we need to generate 2 billion possible IVs. So that becomes much, much larger. So to solve that, let's just look a bit into like how do this thing actually work. So I have a short demo here, which is to show you how system random works under the hood. So we have like just a simple function, which is generate random string, and then we have generate with seed, where you can like specify the actual seed that you want to use, and then you have a function for printing a lot of random strings. So let's just start with the fixed seed thing. So you can also tell I'm not really a developer when I'm running inline C# in PowerShell. This is not the way you're supposed to develop C#. But whatever. So, okay, so I ran this print random strings with fixed seed, which, had this default seed. Where is it? There. Seed is 2. So let's change that seed to 3. We get a different output. And if you didn't trust my slide before, you can see that when I'm running the same thing over and over again, I get the same output. So it's the same, sequence. So if we do that, but let's just not use an actual seed defined. Let's just use the default value, whatever that is. And let's run it a lot of times. And let's first just start with a sleep in between. That shouldn't make any difference, right? And we see that we get different outputs every single time. All right? So if we remove that sleep, does anyone know what's going to happen? Rhetorical question. Let's see. So it prints the same over and over and over again. That's kind of weird. So what is the default seed? Is it a bug in my program? Probably not. If we go to that same documentation, we see that the default seed is the number of milliseconds since the system booted. And all of these that are the same executes in the same millisecond. Okay? So if we go back to this solid bit one, which we had the situation where it sucked that these are different, guess how many times out of 100 they're going to be the same thing? Because they're executed instantly after each other, so 99.99999% of the time they're going to be the same thing. And that's good enough to run it a couple of times. And if they're different, well, it doesn't really matter because we know that it's the next in the seed, right? It's not random. It just follows this sequence every millisecond ticking up. So anyone that's like smart and following what I'm saying now is saying that why do you even need to iterate stuff if you can see the last write time on the file and you know when the system was started? You can actually get the IV that was used, right? Or sorry, the seed that was used. So you don't actually have to iterate this. The problem is that in practice, we figured that that is not really going to work. Because in our experience, we work with incident response with different companies, and pretty much everyone shuts their computer down and don't actually save. So we will not know when the system was booted. And also you have this kind of complex environments where maybe they want to do this in an offline manner, so it's just a drive and we can't get the uptime and so on and so on. And it's, this is quick enough, so we don't have to do that. But, yeah, it would have worked also. And the final step here is, of course, that the seed is known and it doesn't actually use any key derivation like the others at all. So that means that this is going to be super, super fast. We don't even need to have a database file. We can just iterate 2 billion values and do that for every file. Yes. So with that said, we should have gone through all the different ones. Let's see if we can actually try to get our encrypted files back. So I'm not going to click the ransomware again. I am going to take this one. And the reason that I had like underscores for names is because it has a whitelist of the files that it encrypts. And I didn't want it to encrypt my decryptor. So here we go. We install the decryptor. And it says that you need to read the user manual. Please do that, because this ransomware actually installs persistence. So it installs a startup program in the startup programs folder, which is going to start the ransomware again. But in some versions, it's kind of stupid because it also encrypts its own persistence, so that's not going to work. But when you run my decryptor, that's going to work again. So you need to remove that persistence. All right, then we have a license that you also should read. And then we specify the file extension was Onyx, right? Yes. And then we specify the strain. And then we point it to our 8 GB file, which is this one. We do next. Then we can do the entire system, but it's going to take a while. So I'm just going to point it to this folder. And it's done. So here we have the encrypted files, but now we also have the decrypted files. And let's see if this actually worked. And it looks like it did. All right, so I guess we continue from the decrypted file. So it should be the same. And we have now decrypted everything in the entire family. And when it comes to the different, what you do with this, we decided that as a first step, because this was targeting Ukraine, we gave like a heads up to UA CERT. And then after a while, we contacted Europol. And we developed this, and after a while, they actually published this. So in case, Killnet comes into your environment and starts encrypting stuff, you can actually just decrypt everything, which, is good. It's all free. It's also hosted on our GitHub. So if you're curious about the code, or if, you find a bug or something, then please submit an issue. Or if you manage to crack some other ransomware, maybe you can fork it and use that as a base to, use your imagination. So that's pretty much it. Thank you very much for listening.
Thank you very much for very interesting, exciting, and story based on your real experience. And now we have 10 minutes for question and answers. And we have 3 microphones there. So don't be shy. If you have any questions, great, thank you.
Thank you for the great talk.
Thank you.
Just one comment. I think Windows logs the uptime every day at noon in seconds, by the way.
Yeah.
Not that it makes any difference, it will make it hard, but...
Yeah, but absolutely. And that's definitely a good way to do it. It's just, you have like a file system, and it depends on what system actually ran the ransomware, right? Because it's the uptime of the executing system. So you would need to then do that manual, figuring out what system ran it and so on, if there's shared folders and all of sorts of things. But yes, good, very good comment. All right.
Thanks very much for a great talk. My question would be, you did this work as part of your professional work and you're paid by your employer and so on. But do you have any thoughts about the kind of economics of this as a sustainable thing in the future? Like, I wish as a community there was some fund that we could pay people who write decryptors. Do you have any thoughts about that economics and that ecosystem?
Yes, I think it's definitely sustainable. I think it's, I mean, it's important to see that this is maybe not the typical ransomware family. Like most ransomwares is actually using like fairly solid cryptographic implementations, unfortunately. There are some research into other parts, which is not directly like the actual encryption and the mathematics of it. So that is more like how do they decide which files to encrypt, and you have this file share with hundreds of billions of files, or like a ESXi host with terabytes of data. It's going to take quite some time to do all that encryption, because you need to read it, and you need to encrypt it, and you need to write it back on disk. And that's just a natural law that's going to take time. So they take shortcuts. And you can abuse those shortcuts when they try to be efficient. And I think all that kind of thing around that is definitely something that we as a community need to share more and so around. And I think the Europol NoMoreRansom project is a collaboration between private companies that want to share it with the community, basically. But it's also the question of, because it's tricky, right? Do you want to let the threat actors know that you have cracked the ransomware because they're going to change it, right? So it's sort of a, you do that trade-off between helping the victims that have their files encrypted and not letting the threat actors know so they can change their modus. Yes?
Any other question? I know I have a pretty big audience. On Friday morning,
Yeah.
for people more interested in the coffee.
Yes. You will find me at the coffee if you have any other questions. So yeah, thank you everyone for listening.